Okay, I am going to record the answers for problem 7.12. The first thing they're asking us is what is the Earth's angular speed? That's part A. What is the Earth's angular speed? We're told that it makes 1 revolution per day. Okay, so basically this is just a simple conversion problem. Till you get over here till you have radians per second. This is the units they're wanting you to put in, so it's just a simple conversion. Convert revolutions to radians, convert days to seconds. So that's pretty straightforward. I'm not even going to go through and solve that one for you. You should be able to do that. Part B, they are asking, viewed from a point above the North Pole, is the angular velocity positive or negative? Now this, you just have to kind of put yourself up here at the space station. Here's the North Pole. You're looking down on it. Here's the sun over here. Let's think for a second. Now when we see the sun rise in the east and set in the west, meaning the sun appears to travel across the horizon or across the sky from east to west. That tells me that that is the direction that the Earth is rotating. And if you recall, by definition, any rotations counterclockwise are positive. So the answer for this is considered a positive rotation. Now if it's a positive rotation this way, then that means the velocity at any particular point is pointing up, which would make it also positive. Part C, they are asking us, what is the speed of a point on the equator? So now let's look at the Earth from the side. Here's the equator, and we're looking at a point right here. They're asking us, well, actually, let's keep looking down on it from the top for now. Okay, what is the speed of this point? So I want this velocity right here. Well, again, we know that it's going to be positive. We now know omega, because you solved for that up here in part A. So velocity is simply omega r. So you just plug in the omega you found up here in part A, plug in the Earth's radius, make sure all your units square, and till you end up over here with something in terms of meters per second. And I'll just tell you right now, you can go through and figure it out, but on mine, if you have the same numbers that I have, I end up with about 460 if you're following the correct significant digits. Alright, so part D, they're asking for something a little different. They're asking for now, what is the speed of a point on the Earth's surface located at 2/5 of the arc? So now I'm going to look at the Earth sideways. Here's the equator. This was the point we were looking at earlier there on the equator. Now we're looking at some point up here. So if this is a 90 degrees, they want 2/5. Okay, that's not exact. Yeah, that's close enough. Okay, for the sake of argument, we're going to say that this is 2/5 of the angle. So this is 2/5 of 90 degrees. That's the theta. Now let me draw my triangle over here a little bigger, because that's looking kind of tiny. So this basically is a triangle. This is radius from the center of the Earth out to the point on the surface. So that's the point we're looking for the speed. That's the center. This is just a vertical I dropped, which basically comes down there. This theta, I now know, equals 2/5 of 90 degrees. Okay? Because they did say 2/5 of the arc measured from the equator. So I know I'm coming up from that way, not down from the other way. Okay, so what I need to do basically is to find, if this is the axis of the Earth, I need to now know what this distance is right here. I could have done it down here too, but I need to know this distance because that's the new radius. When I was looking at a point out here, to find velocity, we just use omega times r, and we use this full r. But now we're going to have a reduced r because we've moved up a little bit, so now we need this new r. So how do I find that new r? Well, I have a simple triangle here, and so that is obviously the same length as this part of the triangle down here. So to find that length, I would just simply do r. It's adjacent, not opposite, so it's the adjacent side, so it's going to be cosine of and then my angle is going to be 2/5 of 90. So when you substitute in your value for r, take the cosine, that now gives you the length of this piece right here, which is the same as that piece right there, which is the new radius. And sorry, I was off the screen there. So r times cosine of this angle, which is 2/5 of 90 degrees, that gives me the length of this bottom of the triangle, which is the same as this top part up here. So now to find the velocity for this point, I'm just back to this equation now. Velocity equals omega times r. And just for the sake of argument, this ends up to be about, what did I get, about 36 degrees. And so when you go through and you calculate the whole thing, slide it up again, sorry. I end up with, when you substitute in the value for r, I end up with a velocity, omega r, equal approximately 380 meters per second if you follow the correct significant digits. And that makes sense because 380 is less than 460. It's got less of a radius, therefore I would expect it to have less of a velocity. Okay, hopefully that helps.